So what does it mean to create an equivalent capacitor? What we want to do is take our circuit, which has two or more capacitors, though we have to be very careful once we're combining more than two, and we want to turn it into one capacitor. And the reason you're going to do this is that one battery and one capacitor is much easier to analyze than one battery and two capacitors. In fact, the way we analyze two capacitors is by combining it down into one capacitor. Note that you can do this either for parallel capacitors or for series capacitors. And there's actually going to be a simple way to relate our equivalent capacitance, which we write as C for capacitance with the subscript of EQ, meaning equivalent. And there's going to be a simple way that we calculate this in both cases. But the first stage is going to be actually being able to identify whether it is parallel or series, so that's important. And then the equations are actually coming from what we said in the previous video about having the same delta V here and the same Q there. So for parallel, it's quite easy. All you need to do is add them. And again, if you're just getting started on this, I really encourage you to think about only doing two at a time. But you might add more if, for instance, you actually have a bunch in parallel. So for instance, this would be 3 in parallel. I can even add a fourth in parallel. And in this case, you would just say plus C3 plus C4, where C1, C2, and C3, C4 are the capacitance on each of these. And that allows you to make this into just one capacitor with the equivalent capacitance. Now, series, the equation is trickier. Note that this -1 is outside of the entire thing. So some people learn the equation this way because there's actually now a nice symmetry to it. But be careful, you can't just flip all of these upside down. If you think that for series you can write it this way, you're wrong. Please be careful of your algebra. So these are the two different ways of writing it for series. And so again, this might look like you have a capacitor and then you have another capacitor. Series is keeping in mind that you have to march one through the other. And again, here we get to just make that be one capacitor with equivalent capacitance. And again, in this case, we just get to keep adding C3 plus 1 over C4 and so on. So those are the equations, again, being derived from the theory we talked about on the previous video. But what's going to happen is in many cases you're going to have what I would call a more complicated network. Network meaning the way things are connected together. And that means that you're actually going to have a mix of series and parallel. So I'm going to talk you through the rules of how we actually figure this out. So I would call this a complicated network, but as you might notice, there's only 3 components here. It can get much more complicated, and the techniques that we're talking about right now also apply to other components. So when we talk about resistors later, we're going to do the exact same thing with resistors as well, though the equations are slightly different. So what you can't do here is say that they're all in series or all in parallel. Well, why is that? Again, if I imagine my positive charges marching through, they all have to go to C1, but then they get to choose. So I see that there's some sort of series thing happening here and some sort of parallel thing happening. You have to go in the right order or this is going to be wrong. So the first thing that you should do is think about working from the outside in. And the rule I like is that you want to draw a circle and only cut 2 wires with your circle. So let me show you an example of a bad circle because it does not cut 2 wires. Let's say I draw this. How many wires is it? And when I say cut wires, I just mean intersect. It's intersecting once there, twice, 3 times. So this is bad. This is not a good way to group your capacitors. And notice what I was doing here was grouping capacitor 1 and capacitor 3. So this would be a bad one. Do not do that one. Let's try drawing another circle. I can draw this. Notice I have 1, 2. So that's a good circle in that it has two wires, but it's only actually enclosed one capacitor. Our goal is to enclose capacitors into our circle so that we can make them equivalent capacitors. So this isn't useful because only one capacitor is in it. So it's not a helpful circle to draw even though it follows the rules. So the circle you want to start by drawing here is this one. It has two wires that it intersects, and it has two capacitors in it. What this means is that this is your step one. You combine C2 and C3 together. And remember, you can't just add them. Oh, sorry, you can in this case just add them because they're in parallel. So this actually allows us to create one equivalent capacitor, but only for those two. So you need to go step by this. If you only do this in one step and try to do the entire network in one step, you're going to make a mistake. So now that we've done this, we actually need to draw a new circuit. So I've replaced these two with one equivalent one equivalent capacitor. And notice that I've put it where my circle was. So its wires are intersecting the places that my circle originally intersected. So that's how it gets connected. Now we have two capacitors in series, and you know how to simplify that down into a new equivalent resistor. And remember, and I'm going to call that equivalent 2, that's going to go as 1 over C1 plus 1 over C equivalent, because those are in series, and that was the equation for series. So that's how you go step by step. You need to think about going kind of from the inside to the outside. And for some networks, there's more than one order you can possibly go in. For some, not all. But using this rule that you draw one circle and make sure that the circle only hits two wires will be a good way that you can always make sure you're doing it correctly. So briefly, talking through what's going on here, this is how the book does it out. Again, you first take these two that are in parallel and make one equivalent capacitor out of it. And because we got to add them, 1 plus 5 just equals 6. Then we have two in series, and we use that 1 over 3 plus 1 over 6 equals 1 over equivalent, which then gives us 2. We now have just one capacitor, and what you can do at this case is now start solving. What is the potential across this capacitor? What is then the charge across this capacitor? You then can expand it back out into our two series capacitors using that charge and the capacitance of each one. You get the voltage across them, and then you expand it back out again. So this last step is what you would need to do if you were actually asked initially, what is the potential across one of these, or what is the charge on one of these? You actually have to go through the process of making the equivalent and then expanding it back out. But part of why I focused on the process of making the equivalent is that we're going to have to do the same thing for resistors, and that's really tricky and a very fundamental process. So I hope that that helped, and again, you will see these ideas again later, the idea of series, parallel, and equivalence. So do some practice now, and then hopefully it'll make more sense as we also do it with resistors. You're also going to see it in lab, which should also make series and parallel more clear.